Good afternoon, everyone. First of all, thanks everyone for joining this webinar and for your interest in connected vehicles and V2X specifically. And of course, a special thanks to Hackerearth for enabling this. So a little in the way of introduction, my name is Sridhar Reddy, and I run product management at Savari. I've been with Savari for the last almost a decade and with V2X specifically. A little bit about the company. We are a US Silicon Valley startup with our primary engineering office in Bangalore. And Savari is one of the few companies that have been associated with V2X pretty much from technology inception. And today you'll find that our name is pretty much synonymous with V2X. Now, I will tell you that often we end up getting confused with Savari, the taxi rental company. And no, we are not that company. So we're different. We're formerly Savari Networks, but now just called Savari. So with that, today I will attempt to provide an overview on connected cars, specifically V2X, the technology, some application, and its evolution. And I hope that in the end, let's say about 40-45 minutes through this, you'll all pretty much go away with more awareness of what V2X is all about. So before I start, I did want to mention that we have some Savari mugs to give away, and keep questions coming. I think you should be able to see a questions panel in your GoToWebinar. So we're going to give out 5 mugs to the most interesting questions. With that, let me get started. So what is a connected car, right? I mean, I'm sure many of you have heard this term, connected car. And really, what classifies a car as a connected car, or what services or features? So we could talk about internet service, right? I mean, if the car has a hotspot kind of service, I can surf the web, go onto social media and so on. Is that really what constitutes a connected car? What about telematics and diagnostics? What about infotainment, such as streaming music or streaming video? What about navigation with traffic updates, talking about road closures or work zones or traffic jams or flooding, right? What about any safety related features? And finally, what about over the air upgrades, which are much more prevalent today than in the last 10 years? I mean, the reality is that it's really all of the above, right? I mean, it is one or any and all of the above. So this is the loosely termed use for a connected car. Now, an example of connected cars that are well known, let's say our connected car services that are well known, the Onstar from GM started in 1997, the Ford Sync started almost a decade later, and BMW Connected Drive. Now, these are just 3 examples. You have other similar services and features from other car companies such as Volkswagen, Nissan, Hyundai, and so on. Now, if you look at the evolution of the connected car, you could talk about this whole, let's say, era starting with the GM OnStar. But the precursor to that, or rather the main reason for GM starting this, was really for safety. Now, it was post-crash safety, and that's important to differentiate with pre-crash awareness or pre-crash warning, or essentially collision avoidance. So this is an important differentiation which we'll come to later on. So in the beginning, the connected car services were about how do I essentially get first responders to a stranded location, or if my airbag is deployed, what can I do to get emergency first responders there? And then it quickly moved to infotainment, the V2X era, which is kind of been in the works from late early 2000, early this decade, and then in the future we're going to see a lot more bandwidth and uplink and other services based on autonomous cars. So let me take an example of how one of the features works in the OnStar. So you can see you have, in this case, it's a GM car, but it's typically, it's very typical of any connected services model. So you have a car with GPS. So it knows its location and it can broadcast its location based on certain events. Now, what are those events? So for example, your car has its airbag deployed, or it reports a crash because some crash sensors are enabled and they go off. So this information is sent through through a 2G or a 3G connection to the OnStar backend operations, and the operations agent on authenticating and verifying that's really one of the cars as part of the service can then call the emergency first responders. So this is just one example of a feature or a service that's part of the OnStar. Actually, before I go any further, I did forget that we have a very simple survey that will probably just take 10 seconds, which I'd like you to all participate in. You should be able to see this right now and in your window. Essentially, I'm just trying to get an idea of where the participants are from so that it helps us as well in any future webinars. So I'll give it about another 10 seconds, and then we can move on from there. Thanks to all those who have voted. I think we have about 60% of people who voted, maybe just a few more. Okay, with that, I think I can close the poll. Okay, so I'm trying to share the results just in case you're all interested as well. Okay, so let me get back to the connected car. Now, this was the reason so far for connected services, or I should say in the past. Now, what are the big reasons for connected cars today or in the future? So if you think about it, the vast amount of the majority of cars today, especially the high-end cars, have high software complexity. So the GM Tornado, launched almost now 40 years back, had 50,000 lines of code, and this was a huge deal at that point of time. Remember, this was 50,000 lines back in 1977. Cars didn't have that many ECUs back then. So, and if I'm not mistaken, I believe this was launched for a spark timing plug or an ignition timing. Anyway, I don't remember, but the point is it's 50,000 lines, and today a high-end car such as a Mercedes S-Class has about 100 million lines of code. Now, just hold on to that 100 million lines, I'll come back to that. But looking at this kind of complexity, it's not hard to envision why almost 50% of costs in warranty and maintenance have to do with software and ECUs. And also, to give another perspective, the computing power in today's vehicles is almost equivalent to 20 PCs or powerful laptops. So this is one need, and of course there's another need to monetize say after sales, right? I mean, once a car has been sold, typically OEMs find it hard to monetize. I mean, dealer networks do, but back to the OEM, it really makes it hard. So now companies like Tesla have shown that it is, I won't say easy, but it's much more doable than previously thought. So coming back to the 100 million lines of code, I mean, this is an interesting tidbit, at least it was for me. Just looking at other applications, something like Google Chrome has about 5 million lines of code. Each of those vertical lines represents 10 million. And something like Facebook has about 60 million. So between a Google Chrome and a modern high-end car, we're looking at an order of magnitude difference. So this in brief is, I mean, I'm just giving a brief history of connected car and connected car going forward. But the question that we're trying to ask now from now on is, what are the problems that the connected car of today are not solving, right? I mean, we talked about 100 million lines of code. We talked about, OnStar-like features, Ford Sync, and so on. But what is the one big problem that they're not solving? And it's really to do with preventing safety or preventing collision, right? Preventing accidents. If you look at US Department of Transportation statistics 10 years old, and these numbers are not that significantly different. The numbers look closer to 40,000 deaths per year, and this is in the US alone. You have about 6 million crashes, an enormous amount of monetary loss or potential loss, and a huge disaster if you look at from an environment perspective. I mean, almost 3 billion gallons of fuel wasted. Now, what can we do to solve this, or what can connectivity do to solve this? So if you think about your car being able to see or listen to or talk to, if you will, other cars and other nodes on the road. Now, what do I mean by other nodes? It could be a traffic controller, a traffic light, a traffic display sign, a stop sign, anything, or actually everything. If your car can talk to all of that, you can now envision a scenario where you get an advisory or a warning or both, or even a point of time where your vehicle takes control because it has enough information to do so. Now, this is obviously cooperative in nature, right? Meaning I talk, I give out some information and so do you and so on. So it is a shared medium, if you will, and a shared way of helping each other. So effectively, if you see this, I hope all of you are able to see the slides here. If you can imagine a scenario where you see nearby vehicles, you can talk to other vehicles, talk to roadside infrastructure, then you have a scenario where everything's connected. And this is the vision that USDOT, European, similar agencies in Europe, Korea, Australia, and China, and other parts of the world have come up with. So it's really total connectivity of everything and everybody that's sharing the road. And this in the future, or even today, people are trying to extend this to pedestrians, bicyclists, and so on. So what do you require to make this happen, right? What are the fundamental building blocks? Well, a more accurate GNSS is definitely one, and secure wireless transmission is definitely the other. We'll get a little bit more into detail than that. So if you look at the three pillars or the three most important aspects, if you will, of V2X communication, the first one is to do with the radio, the second with the positioning, and the third with security. The first one, the radio, essentially the technology came as a variant of Wi-Fi 802.11a, and it's called Dsrc, or dedicated short range communication. These are direct point to point, or I should say broadcast. So it's peer to peer ad hoc communication for people who are familiar with networking and radio technology. It runs on 5.9 gigahertz. This is a spectrum put aside by most countries in the world, most regions, for public safety. Um, One of the precursors that this technology needs to have low latency. So unlike Wi-Fi, where I start my smartphone or a laptop, try to connect to an access point, and then establish a session, I have nothing of that sort here. I have no association, no authentication. So essentially, if I need to send a message, I send it out, everybody listens, and we move on from there. And the other important part is the range. Now, I don't need kilometers and kilometers or miles, right? I don't need a few tens of feet is too short, because remember, we're trying to avoid safety, trying to warn drivers about potential crash scenarios. So you have to keep the speeds in mind, distances in mind, and the 300-meter range, or just a little over 300-meter range, is what the standards body has said is required. So this is on the radio side and the communication side. Now, in terms of positioning, the most important part is I need to know where my car is within my lane, or rather, I need to know if it's in lane A or lane B or lane C. If I can't distinguish the lane, then it makes it very hard for me to warn another car of potential crash scenarios. We'll get to the security part in a bit. If you look at the spectrum, the 5.9 spectrum, it runs from 5.85 megahertz all the way to 5.925 megahertz. It's 10 channels of, it's 7 channels of 10 megahertz each put aside, and different regions have different, transmit power allowances and different channels that they have stated as for safety and control and so on. And we won't get into that, but I thought I'll just mention this. So what do we need to really transmit? What does one car need to say to the other? What kind of information is important? So the car in the middle, in this scenario, is, think of this car in the middle as just having changed lane from the leftmost to the center lane. So this car is merging in from the left to the center lane, and you have 3 cars in this scenario. Now all of them are talking to each other. Now, what do they really need to say? Well, let's try and figure out if we can just use a little bit of common sense and figure out what these parameters need to be, or what this message set needs to look like. So one of the most important parts is obviously location. I need to know where this car is, right? And if I know my location and other cars' location, then I pretty much know how long I have till I get to that point. I know I can get an idea of trajectories if I have this kind of information, this snapshot in time, right? Let's say 10 times a second or 20 times a second. So essentially, I have my latitude, longitude, and altitude. That's my GPS. I get speed, I have heading, I have acceleration. So I pretty much can now figure out where I am with respect to other vehicles and how quickly I'm moving, what the relative velocities are, and so on. What else is important? Well, vehicle events, right? I mean, think again from a safety scenario. Have I hard braked? Has my airbag been deployed? Do I have traction loss? Am I out of control because there's an oil spill or a flooding, or maybe I have a flat tire, or who knows for what reason? So these are all important events. What about vehicle status? Vehicle size is important. It's important to differentiate between a small sports car and an 18-wheel truck. What about lights? Is the high beam on? Is it lights malfunctioning? Perhaps the lights are not working, right? Or what about turn intent? Am I trying to turn left, trying to change lanes? So this kind of information is also very important. And then finally, if you think about how we all drive, um, you don't stick to your lane and you don't essentially go in a straight line, right? The roads have curvature, you take U-turns, you go around roundabouts or circles. So if you look at the white cars here, they're trying to show you what the trajectory of a car could look like over time. So it's important to know whether I'm on a curved road, am I going on a curved path, a U-turn, or a circular, or a right turn or a left turn, and so on. So I kind of have to know my path intent for, let's say, 100 meters or 200, 300 meters. I don't really need to know it for much more than that. So essentially, think of it in a short duration. Where am I going? Where did I come from? And what do my road curvatures look like? So it's these parameters. So it's this kind of information that's most crucial. There's some other parameters as well, but I won't get into that. And at this point, if you have followed what I've just talked about, then you should all congratulate yourself, because this is nothing but the basic safety message. So this is the most important message within the V2X domain, and it's also called the BSM. There are other messages as well. For example, the traveler information message, a SPAT and map. The traveler information message essentially gives you information about that you can see on the road, on traffic display, traffic signage, and so on. SPAT and map give you information such as signal phase and timing, and map information. So you could get an idea of whether it's green light or red light, and how long do I have for green, how long do I have for red, and so on. Now let's get back to the V2X communication part. We did talk about how there is no association. Radios can transmit over the air whenever they have messages to send. So this is all broadcast, right? Which also means it's not guaranteed. I mean, since there's no session, there's no point to point, there's no specific overall, guaranteed session. I can't guarantee transmission. And also, because these messages are sent often enough, for example, the BSM is sent 10 times a second, I don't really require retransmission. I mean, you could argue that perhaps, in certain cases it's useful, and yes, there are cases, but for the most part, you don't require it. So that comes down to how often should you transmit, and there's different specifications here. Some regions talk about sending it 10 times a second. Some regions talk about sending it when there is a need to send it, which means if you're moving fast, you send it more often. If you're moving very slow, then you send it less often, right? So that makes sense. Now, in terms of positioning, the accuracy defined, remember, is a lane level accuracy. And what kind of accuracy do we require for this? Well, you could argue that I need to know whether I'm in the lane, so I need half the lane width. And that's where the plus minus 1.5 meters comes in. And that's also the reason why you don't need, I mean, something like 2.5 would be too much, because 2.5 meters on the left or to the right would put me at a total of 5 meters, which is beyond the lane width. A typical lane width is about 3.5 meters. So, so you have 1.5 meters, positional accuracy, and then security. So What's really important in the security? If you think about it, this whole information is not private. It's not a secret, right? The information that you're sending out in the BSM is really for everybody to consume. Remember, this is cooperative technology. So if you were to keep it private, it's like driving on the road with some kind of cloaking device that nobody else can see you. So that doesn't make sense. The whole point is that people see you, are aware of you, and take action, right? And that you're all sharing the road and you all have to do it in a safe mechanism. Now, the security in V2X is pretty much along those lines. It's not meant to be private or secret or encrypted. Instead, the whole goal here is for the transmitter or for the transmitting device to be authorized. So you need to be an authorized device, which means you need to have gotten your certificate from some central agency. So you need to be authorized to be able to send messages, obviously receive messages, and the authority has, in the event that you misbehave or you become a rogue agent, you're sending false messages, for example, then the authority, the central authority, has the right to revoke your certificates. So the one crucial thing here to remember is in V2X, anonymity is preserved. There is nothing in these messages that identify a specific vehicle or a specific driver, but instead it's more about sending messages about a vehicle, right? And a specific object that's moving with certain characteristics. So that's one crucial part to remember, is that it's really anonymous. So with that, oh yes, and I forgot, the entire security system is based or is modeled after a public key infrastructure. It's, as I said, authorized transmitters, central authority. Information is not private, but it is anonymous and it's not trackable. So I cannot track a specific vehicle based on the messages that you've been sending me. And clearly the information is not a secret, right? Okay, so with that, let me give you an idea of what some of the applications look like. I think, if I see the poll, I have almost half the audience here are from the automotive industry. So, I'm sure most of you are familiar with these scenarios, or even if you're not, these are pretty basic, right? You have your intersection collision scenario where you're colliding at almost right angles to another car, and this is one of those scenarios where you can't really see the other car because it's coming out of a right angle to you. You also have blind spot, wherein you have adjacent lanes, specific regions which are in a blind spot and you can't really see a car in that region. And you have your forward collision warning. Again, this is just a very small sample set of possible applications. Now this is vehicle to vehicle, hence V2V. Now you can see V2I, vehicle to infrastructure. And this has to do more with how do I communicate traffic signs, traffic light, signal phase and timing information, work zone alerts, and possibly tolling. This is, again, as I said, a very small sample set. So overall, if you look at number of V2X applications, again, this is only one set of many. And just putting it out here, not for you to really read, but it's just to say that there's tons of applications. And really, in the future, I would expect these applications to grow and it would be very similar to what, say, a smartphone application could look like, right? I mean, there's millions of applications today. So if not millions, at least thousands of applications. Now, we come to one of the most important use cases for V2X. Now, what is that? Now, this is for a self-driving car. Now, I'll just take a minute here to talk about different levels of autonomy. When people talk about a self-driving car, it's, that's the holy grail of the self-driving car, is really to put your 5-year-old kid and have the car just drive from point A to point B. So if most of you are in Bangalore or wherever, whichever city, right? Or I could even say, I put my kid in here in Bangalore and I need to get my daughter to, Hyderabad, where my parents live. And that's really the goal, I mean, the holy grail of a self-driving car. And that is level 5. Level 5 autonomy requires absolutely no human intervention. Level 4, if you work backwards, is pretty much the same capability, but in certain specific conditions. For example, highways, right, or cordoned off roads, or maybe during certain times of the day, right? So that is level 4. Level 3, where you're shifting many of your safety critical functions to the car, to take autonomous decisions, but you're very much required, and you're not shifting all of them. Level 2 autonomy is pretty much that you are using one safety feature, could be something like cruise control, except that it's like something like adaptive cruise control, where you're using the environment to adjust and to adapt. Level 1, you essentially have a simple ADAS function like steering or acceleration, but with no awareness of environment. And level 0, where you have absolutely no autonomy. So these are the 5 categories, if you will, of autonomous driving. Now, why is V2X important, right? The reason I mentioned all this here is the biggest differentiator, if you think about V2X, is that it's non-line of sight sensor. It is another sensor, just like a LiDAR or a radar or a camera, except it's the only non-line of sight sensor. So it's crucial for path planning for self-driving cars. And that's the reason that V2X is a certain requirement for level 5 and even for level 4. Now we'll talk about a competing technology for Dsrc called Cellular V2x. Now, about a couple of years back, this competing technology was introduced based on 3GPP release 14. The one thing I want to mention is Cellular V2x is a very broad term, and the CV2X that people are talking about today in terms of pilots, trial, and availability is really LTE V2X versus the more upcoming 5G V2X. And the 5G V2X will be called NR V2X for new radio or next generation radio. And that's for 3GPP release 15 and beyond. I'm sorry for apologize to the audience who are unfamiliar with these terminologies, but I think the telecom and networking land is full of acronyms. Now, this is just a snapshot of 5GA members. 5G is the 5G Automobile Association, or primarily driving the CV2X technology here. Just to show you that pretty much all the big heavy hitters are all here: semiconductor suppliers, wireless radio suppliers, and so on. Okay, so 3GPP has 2 modes of communication. One is called the UU interface, and one is the direct interface called the PC5. The direct interface is equivalent to Dsrc, where you have ad hoc communication. A vehicle has something to send, and it just sends it to everybody else in that vicinity. One of the crucial differences here is the applications and use cases that can be enabled by different modes. For the UU interface, you only look at applications that have high latency tolerance. For example, few seconds, few tens of seconds, maybe a minute, maybe a little higher. So this is where, for example, I'm coming, into a region of let's say traffic jam, 2 miles ahead or a mile ahead, or even few miles ahead, right? And then I get this information through an LTE base station by connecting to the network. So essentially, I don't talk direct to other vehicles, but I talk through the network. So that's an example of a UU interface application. PC5, on the other hand, is like your Dsrc. It has a similar applications, except it has a higher range. So the range can go up to 1 kilometer. It depends on the environment, depends on weather, depends on everything else that's happening there. But predominantly, it's about a 1 kilometer range versus Dsrc at a few hundred meters. Now, the use cases and applications enabled here are very similar to Dsrc as well. So I won't go more into detail here. And finally, for autonomous driving in the future, this is just to give you an idea of the kind of bandwidth that's required. Today, LTC, V2X, and so on only give you, low tens of megabits. Now, in terms of use cases for platooning, advanced driving, remote driving, if you look at this is hugely, very heavily bandwidth intensive. And you're looking at up to 1 gigabits per second. Now, some of you may think that's insane, but this is how technology seems to be progressing. Now, this is a view of different services or different use cases that are possible when you are on the road and you're looking at whatever, you're looking at different participants within the network. So you have vehicle to vehicle with other vehicles, you have vehicle to infrastructure with your traffic lights, vehicle to network, for maybe real-time traffic, cloud services, and so on. And finally, vehicle to pedestrian through your smartphone. So your smartphone actually, when 5G is all enabled and is prevalent and available, the smartphone becomes a powerful enabler of future 5G services. So with that, let me try to see if I can show you a video. I hope that the network latency is going to give us a break here. Just bear with me for 1 minute while I load up the video. So this video is showing you a series of demonstrations where it runs through different scenarios, collision or safety scenarios such as emergency brake light, left turn assist, signal phase and timing information, vehicle to pedestrian, intersection collision avoidance, and stationary vehicle warning. So with that, let me try and start. This scenario here is an emergency electronic brake light where the car in front, not immediately in front of you, but all the way ahead, does a hard brake, and all the cars behind this car receive this information. So this is a powerful use case wherein you avoid typical pileups. And now you look at a left turn assist where the car slows down and takes a left after the motorcyclist has passed them. Well, I think the presentation will be available anyway later on, and then for those interested, they can click on the link and watch this. So let me go on to the last few slides here. A little bit of information about CV2X versus Dsrc. So you heard a little bit about CV2X and Dsrc, CV2X being the more relatively newer technology. So CV2X provides a longer range, better SNR performance in terms of the radio. It also has higher tolerance for higher vehicle speeds. I mean, I think it can still work at the speeds of 500 kilometers an hour, which seem outrageous, but well, as far as technology goes. And what else? I mean, CV2X with release 3GPP release 15 and 16 will provide for much higher speeds than today's release 14. Now, on the flip side, Dsrc has almost a decade proven experience and field trials. A lot of research and work has gone into it. And even the NHTSA, if some of you have heard of it, the National Highway Transit Safety Authority, the safety wing of US DOT, has sent out a pre-mandate for Dsrc to be put into production cars in the US. So Dsrc has also been deployed in production cars in the GM Cadillac, and there's more programs announced, right, by different OEMs. So if you look at the publicly announced OEM preferences, and again, these are just preferences, and this is just a short list On the DSRC side, you have Volkswagen, Toyota, and GM. On CV2X, you have companies such as BMW, Audi, and Ford. V2X across regions, what are the main, the big differences, if you will? Well, the spectrum's pretty much the same. It's 5.9 gigahertz in these three regions: North America, Europe, and China. But you have differences in terms of what OEMs have done with different technologies. So DSRC, as I mentioned, has been deployed in the GM Cadillac 2017 model. Europe has recently passed a delegated act, which is much more, let's say, inclusive for DSRC. And this still needs to be ratified by the European Commission, which I believe is a few months out. In China, there is no DSRC, and they've gone completely to CV2X. Production's underway in China by multiple OEMs with CV2X equipped cars starting as soon as 2020, so model year 2021. North America also, companies like Ford have shown a strong interest in CV2X, and Europe, companies such as BMW, Audi, and so on have also shown that same interest. Now, in terms of standards, they're loosely known as WAVE standards for North America, HCITS for Europe, and China SAE or CSAE standards for China. They're also called GB standards in China. The production programs I've talked about in terms of timeline. And one last thing that's interesting is the main precursor, the main driver for V2X, I should say, is really different for different regions. In North America, it's safety. In Europe, it's mobility. In China, it's really road automation. So finally, this is let's say, an aerial view, if you will, of what future 5G unified connectivity would look like. Essentially, it connects all users, use cases from low speeds to extraordinarily high speeds. We're talking 1 Gbps, high latency to high speed and low latency. So it's really a combination of, you pretty much can have any service, including HD video, virtual reality. I mean, the scenarios that people are talking about is really, it seems like it's coming out of a science fiction movie. And people are talking about remote driving, where I essentially operate a car remotely through a high bandwidth connection. The other interesting part, or the other, I would say, inclusive part for pedestrians, is that they can now be part of that ecosystem as well, provided that 5G chipsets and 5G phones are, also enabled with V2X. So this itself is a very powerful enabler for V2X overall. Now, with that, I think we've pretty much come to the end of my presentation for V2X. Again, as I said, a little bit about Savari. We do a lot of this work. We are some of the pioneers of having done V2X work, both in DSRC and CV2X. We work with partners, with preferred vendors for partners such as Qualcomm, GM, SAIC, and so on. So, we are very shamelessly advertising that we are hiring. So if there's any interest, please do look us up. With that, I will take some questions, but perhaps before that, I have one survey. So please do keep questions coming if you haven't typed them out already. Okay, so I'm already seeing some questions. I'll get into that in a bit. I have one survey to provide. So I've just launched it, and you should be able to see it now that you know a little bit about the V2X industry. So I would again appreciate your participation in this. Okay, I think we have 55% voted. I'm just going to give it another 20-30 seconds. Okay, with that, I believe most of you have voted, maybe a few more left. All right, so with that, I'm going to close the poll. Okay, so on to questions. Okay, the first question is, are we talking about all cars in general or self-driving cars in specific? So I'm not sure what the context is here, but V2X is for all cars. The importance and the use cases are obviously different in different cars. So a self-driving car, would use or could use V2X in a different way. For example, as I said, path planning is something very specific to a self-driving car. whereas path planning in a regular car or a non-self-driving car is done by the human, by the driver. So I hope I've answered that question. So really the answer is V2X is applicable for all cars, and it has to be because it's cooperative technology. Second question is, if my accident took place in between a road which is covered by two buildings, then in this situation, GPS will fail. How can we send a message? Okay, very good question. So essentially, if I don't have GPS coverage, and the question here is talking about if I'm between two tall buildings, but really the question is if I'm in a basement, in a tunnel or under a bridge. I mean, all of these situations can cause a loss in GPS. Now, this is definitely an area of concern. I haven't really talked about challenges here. There's you could say there are many. Now, you can't solve all this in one day. Now, people are looking at things like dead reckoning, inertial navigation, where you can provide a reasonable degree of certainty for 100, 200, 300 meters distance. Now, where you have problems, especially in areas like tunnels, let's say 1 kilometer, 2 kilometer long tunnels, you could look at repeaters. So there's different options that people are looking at. And again, this whole ecosystem of providing this kind of facility will take time. So it is not something that we would expect to see on day one or even the first 2 3 years. The point is that if you're still able to enable safety 80% of the time, that's still going a long way in terms of saving lives, right? And that's really the idea here. There's also one more thing I wanted to mention about GNSS. Some countries have already moved to dual frequency system where urban canyon problems have been mitigated. So in places like, say, Bombay or even parts of Bangalore or, let's say New York, San Francisco, Tokyo, in these places, you pretty much have absolutely no GPS certainty. You have GPS coverage, but really because of urban canyon effect, you could be your position could be shown as nearly 2 blocks away from you. So how do you solve these? And there are various ways to do that. I mean, I won't talk about it now, but one of the ways is to have multi-spectrum, higher priced antennas, more expensive, but it can definitely be done to a large extent again. The question is, can we use connected cars concept even for ships and flights? Well, connected cars, really think about the range. When you think about use cases, think about what the radio and the technology allows for. So if you're talking about 300-400 meters, then it doesn't make sense for ships, and neither does it make sense for flights. But if you're talking about, say, something like drones, definitely for drones, you could have a mesh network, or you could have information exchanged between drones. Again, safety-based information with, say, let's say a 1 kilometer radius, right? And that's still long enough and definitely a useful use case. Okay, another question. If two cars collide with each other, both will send message to GPS system using radio waves. Both cars are near there, waves may get trapped in interference, and due to interference can distribute message. What will car do in this condition? So I'm not sure I understand the question. I think the point of V2X here and the point of connected car systems is you send the message, well, you send each other, you try and avoid the crash scenario if possible. If you can't avoid it, you can do things like prepping the airbag and maybe automatic braking and so on. But there will still be those scenarios where you end up with a crash situation. But the messages that go out have really nothing to do with interference. I mean, this is all broadcast medium, and depending on where you're sending the message to, it just depends on connectivity back to the network. Let's see, another question. Can we use connected cars concept to find lost or missing flights? I think I've answered the question on flights. Is it not possible to use 4G network? So if the question is more with relevance to can't we use 4G to have replicate V2X? The answer is, well, 5G is trying to do that, but in 4G or even with any older technology, you're not guaranteed of any latency here. I'm not guaranteed even to be able to send a message. Remember, it's a any message, any session relies on higher level or higher layer application to retransmit and ensure that your messages have gotten through. In a scenario where I just need to send my information, and think about as real-time application, like voice or data, voice or video. If I'm having a live voice call, there's no point trying to retransmit my voice data after say 100 milliseconds or 200 milliseconds, right? So it can survive some amount of voice can survive some amount of packet loss, but when you're sending basic safety messages, you need a more reliable system, right? Wherein you're sending shorter, small messages more frequently. Not much is changing between those messages, but you also don't need the flex. You don't need the long range that comes with 4G and so on. Because you're only worried about your immediate environment of say a few hundred meters. Um, Can the connected car concept be helpful in finding any problem in the vehicle? Well, this is definitely the connectivity itself definitely can do that. Well, you can do that by enabling diagnostics and relaying this information back. For example, I have a battery that's going to die, or a puncture maybe, or something else that's going to cause a massive failure in the engine. Definitely these pre-failures, or any data that looks like I'm going to suffer a failure in the next few hundred kilometers or few thousand kilometers, this information is definitely useful to have, is part of telematics today in some cars, and this information is definitely sent back to the to the server, to the telematics server. Let's see. Okay, I'm just looking through some questions here. There's lots of questions, so I'm avoiding some which are perhaps not relevant to what we talked about. Okay, interesting question. What will be the power consumption difference between Dsrc and CV2x? So, in terms of the radio alone, CV2x definitely has slightly higher power consumption, but I don't frankly know what the difference is in terms of actual numbers. I don't think, however, that this is materially significant. But having said that, I'm not really sure. How effective is this among hackers? Well, like anything else, I think determined hackers can perhaps always find some ways to break into a node or spoof vehicles and so on. But there is a lot of work that's happening in the security standards to prevent exactly this. And there's something called misbehavior detection, wherein if you encounter basic safety messages from other vehicles which don't seem real, then you start avoiding or ignoring those vehicles. And there's mitigation ways to do that, and that's part of misbehavior reporting and action. How is the regulatory framework coming up? So as I said, the NHTSA in the US has a pre-mandate in terms of NPRM. The European Union recently passed the Delegated Act, which still has to be ratified by the European Commission. So that would make it pretty strong. And China has pretty much given a mandate within the country. So depending on the region you're talking about, there is different regulatory framework. I should say more in terms of standards. There is no mandate yet in any region that I'm aware of. So no government has come out and said you have to deploy V2X, in production cars starting 2022 or whichever year. So that hasn't happened yet. Can Dsrc and CV2X communicate with each other? No, they can't. Even though they're in the same spectrum, it's completely different radio technology. So it's almost like, can Wi-Fi and something else, Bluetooth, communicate with each other? No, they can't. But again, there are, agencies and, organizations that are looking at using both radios and doing a relay between both these radios. Okay, what is the contribution of Wi-Fi in autonomous cars? Well, Wi-Fi itself doesn't have much relevance except for Wi-Fi connectivity within the car. So from a safety or mobility perspective, Wi-Fi itself doesn't have much of a role to play. So instead, you would use something like Dsrc or CV2X between autonomous cars. Question about V2X for two-wheelers. Are there any pilots in this area? What about the implementation challenges when it comes to budget cars in India? Does it make sense? Okay, very good question. So in India, we have, our challenges are different, right? I mean, when we talk about safety in the West, where they're trying to deploy V2X, you're talking about cars, maintaining a safe distance for the most part. It's really hard to talk about any application or safety, um, features in place when we're all driving within a feet of each other, right, within a foot. So somebody I talked to in a conference once said, well, if we're all intent on killing ourselves, there's very little that technology can do. So I don't know if I've answered that question, but that's really where it is. What if not all vehicles in the path follow the V2X infrastructure? Will those cars with V2X still work? So good question. Will the cars with V2X still work? Now it depends on the use case. So think of it like like a cell phone, right? In the starting days of, in the mid 90s, when the cell phones just came out in India, if only a few people had it, right? Then the number of use cases that you could apply would be very different. So similarly here, if you essentially have 5-6% penetration, certain use cases such as EEBL, which we talked about, emergency electronic brake light, where somebody ahead hard brakes and cars behind are notified of this hard brake, that is useful irrespective of whether everybody has it or not. I mean, I can make an argument that that use case is very much valid even if I have only, say, 5% of cars equipped with V2X. On the other hand, if I have to look at something like forward collision warning, then it makes sense only if the other car in front of me has V2X. So the answer to that question is it really depends on the final application use case, uh, and that determines whether it's useful or not depending on the penetration. Okay, if DSRC and CV2X are solutions, why is an autonomous vehicle required? Well, the DSRC in CV2X is really about connecting and communication between cars. Autonomous vehicles are more about just taking the human driver element out of it. So if I want to go from one place to another, I can essentially sit in the back seat, not have a driver, right, and move, go from point A to point B. But beyond that, there are different ways to monetize a vehicle where I don't have a driver to pay, right? And so companies like Uber, um, yeah, and Lyft and so on are looking at autonomous car technology specifically for that reason. Because Uber pays 75-80% of the charge of the end, price, a ride fare, to the driver. Now, if you didn't have to pay this, instead you used a self-driving car owned by Uber, then you could essentially monetize the entire, ride ticket. So that's one of the reasons for autonomous cars. Um, let's see. Some more questions. What happens when non-DSRC vehicles enter infrastructure? I mean, old vehicles. Um, Really not much. There are aftermarket units that can be deployed once V2X penetration starts, and you could be part of the old car can be part of the V2X infrastructure. Obviously, I talked about penetration. So if they don't, then yes, you can't make use of it, and neither do the V2X cars make use of your information. Um, V2X will be implemented in new production cars. Do you have anything in your mind to implement this technology in existing cars without any changes? Yes, that is definitely possible, and that's part of the aftermarket units. What are the use cases which can be done using V2X but can't be done with autonomous car sensors? So anything that is non-line of sight can be done with V2X. That cannot be done with traditional lidars, radars, and so on. I think there's one more survey, probably the last one. Let me see. I think we have 2 or 3 more questions. Can we get drive quality data from V2X? Absolutely. And this is a big use case for insurance industries. So I could make out, I can get information like how much is he swerving in the lane, at what yaw rates, and what, how rapidly is he taking lane changes, turnings, um, are you hard braking, are you accelerating very hard? So definitely insurance agencies are interested in this information. I guess the last question here, Shouldn't the technology be used throughout any car and the driver's mobile when in a car? Not sure I follow this question. Shouldn't the technology be used through any out of the car and the driver's mobile when in the car? So, sorry, for the person who asked that, I'm not sure I follow the question, but you're definitely welcome to send that to me. Okay, so I think that's pretty much it. So there's some other questions, but I think we are close to running out of time, or we have run out of time. Any other questions that you folks have, feel free to email me. I'm happy to answer any questions that you have, right? And thank you for your interest, and thanks for joining. Good luck. Bye-bye.